Right. This is question number 1. Enthalpy of reaction for the following is hydrogen gas combined with the chlorine gas form 2 moles of hydrogen chloride. For this reaction, enthalpy is given minus 150 kilojoule per mole. Calculate the enthalpy of formation of hydrogen chloride. Listen, we all know that enthalpy of formation means it is the amount of heat absorbed or released when 1 mole of a compound formed from its elements in their stable and naturally existing state. Okay, yeah, hydrogen is an element, this is also element, they are all naturally existing, stable as well as in their naturally existing state. Okay, but here it produces 2 moles of hydrogen chloride. What is enthalpy of formation? It is the amount of heat absorbed or released to form 1 mole. Okay, so what you have to do? To form 1 mole, I have to divide or multiply throughout by half. Half H2 gas plus half Cl2 gas, so that I will get 1 mole of hydrogen chloride, HCl gas. Okay, so this is the reaction which we want actually. For this reaction, what is delta H? That delta H is nothing but enthalpy of formation of hydrogen chloride. What is the value? The value is very simple. Okay, this is for 2 mole, right? For this enthalpy is for the formation of 2 mole. For the formation of 1 mole, what to do? Divide the value by 2. So minus 150 by 2 will give me minus 75 kilojoule per mole. Kilojoule per mole. Okay, so this is the answer for this question. So if question is given like this, just see whether 1 mole is formed or 2 mole is formed, and see the elements in their natural state or not. Okay. Then to form, see here in this problem, to form 2 mole, 150 kilojoule of energy is released. Then to form 1 mole, how much you have to calculate? Okay, yeah. Take it. This is problem number 2. Which among the following has standard enthalpy of formation value 0? Okay, see, just go through all the given species, all are elements, right? We know very well, standard enthalpy of formation, okay, for elements in their stable and a common occurring state or naturally existing state. Common occurring state, okay, is 0. Keep this in mind. Standard enthalpy of formation for elements in their stable and common occurring state is 0. Now what are the species given? Mercury, but it is given solid. We all know, see, mercury solid is given. We all know mercury exists commonly in the liquid form. Therefore, for this mercury solid, standard enthalpy of formation is not 0. It is not 0. It is not equal to 0. Right? Then second one. Whereas if you take liquid mercury, which is the common occurring form of mercury, for liquid mercury, yes, it is 0. Okay. Then second element, red phosphorus is given. For red phosphorus, standard enthalpy of formation is not 0. Why it is not 0? Then we know very well. In red phosphorus, we have 3 common forms. What are they? Black phosphorus, black, red, and white. If you compare their stability, black phosphorus is more stable than red phosphorus is more stable than white. But if you see their common occurrence or the abundance is very high for white phosphorus. Okay, therefore, since abundance is high or the common occurring state is for white phosphorus, so in the case of phosphorus, for white phosphorus, okay, standard enthalpy of formation is given as 0. Keep this in mind, very, very important. Okay, common occurring state for phosphorus is white phosphorus only. Right? So, for white phosphorus, the standard enthalpy of formation is 0, not for black phosphorus. Keep that in mind. It's a very important one. It's an exception actually. Okay, try to remember this. Then, the next element, what is the next element given? Carbon diamond. We all know diamond carbon, and if you compare with graphite carbon is more stable compared to diamond. Therefore, for diamond carbon it is not 0. Whereas if you take carbon graphite is called carbon graphite, it is 0. Okay. Then the next one, right here. Next one, monoclinic sulfur is given. If you compare rhombic sulfur and monoclinic sulfur is more stable. Therefore, for monoclinic sulfur it is not 0, whereas for rhombic sulfur it is 0. Keep this in mind. Then for iodine, yes, if you compare halogens, you know very well fluorine exists in the gaseous state, chlorine natural existence is gaseous, right? Bromine exists naturally in liquid state, whereas iodine naturally exists in a solid state. So here iodine solid is given. Iodine solid is given. Yes, the standard enthalpy of formation is 0 for iodine. Okay, then for hydrogen, you know very well the common occurring state of hydrogen is not liquid. Here, in the given question, liquid is given. Okay, for liquid, this is not 0. Right? Whereas if you take a gas, hydrogen gas, H2 gas, for H2 gas, yes, it is 0. It is 0. Are you able to follow? Right? Keep this in mind. Right. The next question is, calculate the standard enthalpy of combustion of toluene using the following data. Standard enthalpy of formation of carbon dioxide is given. Standard enthalpy of formation of water is given. Standard enthalpy of formation of toluene is given. Okay. Right. Now we need to find out the enthalpy of combustion of toluene. Okay. What is combustion? You know very well. Toluene, this is the formula. The methyl group is attached with the benzene ring. Okay, and molecular formula, it contains 7 carbon, C7, and here 5 hydrogen, here 3, so 8 hydrogen. So C7H8 is the molecular formula of toluene. Toluene exists in the liquid state. Now, combustion means burning with oxygen, right? So, if it reacts with oxygen, what will happen? We all know that whenever an hydrocarbon burnt with oxygen, all the carbon become carbon dioxide and all the hydrogen become water. Okay, liquid water. So I have 7 carbon here, so put 7 here, and I have 8 hydrogen, so put 4 H2O, so that hydrogen get balanced. Now to balance oxygen, see here 7 into 2, 14, 14 plus 4, it is 18, so I'll put 9 here. So this is the balanced equation. Okay. See 7 into 2, 14. 14 plus 4 oxygen here. So 14 plus 4 is 18. So 18 oxygen atoms, so I put 9. Therefore, it is get balanced. Now, this is actually called combustion reaction. The enthalpy released or absorbed, or heat released or absorbed in this reaction, okay, is nothing but enthalpy of combustion of toluene. How to get this? Listen, it's very simple. If you know enthalpy of formation of all these species, you can calculate enthalpy of combustion. So, enthalpy of combustion of toluene C7H8. This is what we need to calculate. This is equal to enthalpy of formation of the product, summation. We all know enthalpy of formation of product, right? And you have to multiply this by number of moles of the product minus enthalpy of formation of the reactant into enthalpy of formation of the reactant. Number of moles of the reactant and enthalpy of formation of the reactant. Right? And here it is given standard state, so put standard condition. Everything in standard condition. Okay. Yes. So how to get this? See what are the species we have in the product side? In the product side, we have carbon dioxide and water. How many moles? 7 moles. So 7 moles of carbon dioxide. For carbon dioxide, enthalpy of formation is given. Enthalpy of formation of carbon dioxide is minus 393.5. So I'll put that minus 393.5. Okay. Plus the next product is water molecule. I have 4 moles. So 4 into, for water, the enthalpy of formation is minus 241.8 kilojoule per mole. Okay, so these two are for product. Minus, if you come to reactant side, in the reactant side, we have toluene and oxygen. Okay, oxygen is in the gaseous state. For toluene, we have only 1 mole here, 1 mole, so 1 into standard enthalpy of formation of toluene, which is given. Sorry, let me write it. 1 mole into standard enthalpy of formation of toluene is given, which is plus 70. I'll put that value as such. Plus, and the second reactant species is oxygen. You know very well, standard enthalpy of formation of elements in their stable and common occurring state is 0. Therefore, this is 0. So what we get is, right, we have to multiply all these things. Let me do it. So 7 into minus 393.5. Will give me a value of minus 2754.5. Then you have to multiply here. This will give me minus 967.2 kilojoule, and here we have minus, and here minus of this, so you get minus 1 into 70 is 70. Okay, now all are the same, all are the same sign, so we have to add. Yes, it comes out as minus 3791.7 kilojoule per mole. Okay, this is the standard enthalpy of combustion of toluene, C7H8. Okay, this is how we can calculate, right, using this given data. Okay, so if a problem is given like this, right, first see what is the reaction, for which reaction we need to calculate the enthalpy change. Write the reaction clearly with it, and you should balance the reaction carefully. Okay, you should write the balanced equation, right? Then if the enthalpy of formation data are available, you can calculate this enthalpy of this reaction using this formula. That is total enthalpy of formation of the products minus total enthalpy of formation of the reactants. Okay, right? Yes. Yeah, next question is question number 4. Calculate the standard enthalpy of formation. Now, they are asking standard enthalpy of formation of sucrose using the following data. Okay, some reaction is given. Say this is sucrose, C12H22O11 solid. Sucrose is burnt with oxygen and gives carbon dioxide and water. For this reaction, enthalpy is given. This is called enthalpy of combustion, correct? Enthalpy of combustion of sucrose. And the enthalpy of formation of CO2, enthalpy of formation of water, these two data are given. Now, using this, you have to calculate enthalpy of formation of sucrose. Yes, how to do that? It's very simple, listen. Here, sucrose in the left hand side, right? Reverse the first reaction. Just reverse the complete species present in the first reaction. So, what we get is, listen, 12 CO2 gas plus 11 H2O liquid will give C12H22O11 solid. This is sucrose plus 35/2 O2 gas. Okay, I just reversed the first reaction completely. If you reverse the reaction, you know very well, according to thermochemical laws, whenever you reverse the reaction, then enthalpy of the new reaction is nothing but the same value of the original reaction, but opposite sign. So instead of minus, you put plus. Okay, plus 3000 kilojoule per mole. Okay. Whenever you reverse the reaction, the amount or magnitude remains same, but the sign will change. Okay. Now, listen here. See this reaction. We are getting sucrose, 1 mole of sucrose. So this is what we call as enthalpy of formation. Okay, enthalpy of formation. How it is enthalpy of formation? Yes, we will discuss. First, reverse the reaction and get the required compound in the product side. Now, sucrose is forming, right? Now, what I am going to do, we have to cancel the CO2 and H2O, and we should bring carbon and hydrogen and oxygen in the left hand side. How to do that? That's why the other reactions are given. Now, listen, the second reaction, graphite carbon, oxygen combined with CO2, right? Delta H naught is given. Now, what I am going to do, I have 12 CO2 here. I have 12 CO2. So, what I am going to do, I will multiply this throughout by 12. So, what we get is 12 carbon graphite plus 12 O2 gas giving 12 CO2 gas. Now, if I multiply any reaction by a constant, then the enthalpy should also be multiplied with the same constant. So, enthalpy of this reaction, delta H naught equal to, we have to multiply this by 12, gives me minus 4722 kilojoule per mole. Okay. Now, what is the third reaction? Third reaction, H2 plus half O2 gives H2O is given. And here we have 11 H2O, so we have to multiply this reaction throughout by 11. So let me do that. So 11 H2 gas plus 11 into half, 11 by 2 O2 gas giving 11 H2O liquid. Okay, now what to do? I have multiplied this reaction throughout by 11, so multiply this quantity by 11. So if I multiply the delta H naught by 11, we get equal to minus 2659.8 kilojoule per mole. Okay, so what I did, I reversed the given reaction so that sucrose is coming in the product side, because we need to find out enthalpy of formation of sucrose. So bring the sucrose to the right hand side, then multiply this reaction by 12, because we need 12 CO2, so we have to multiply this by 12, and here we have 11 H2O, so we have to multiply this by 11. Okay, now after multiplication we get this equations. So what I am going to do, I am going to add the equations. While adding, if you have same species, you can cancel. Okay, yes, I have 12 CO2 here, and the right hand side also I have 12 CO2, so let me cancel that. 12 CO2 cancel, 11 H2O cancel. Then what is remaining? Let me write here. Remaining species, I have 12 carbon graphite plus 11 H2 gas. Okay, then we have 12 plus 11 by 2, which is 35 by 2. 35 by 2 put to gas will give C12H22O11 plus solid plus I have 35 by 2 O2 gas. Sorry, I didn't cancel that oxygen. Now let me cancel it. If I, 1 second. Okay, sorry, in the given reaction, the data is wrong. Let me read carefully. Listen, here we have 12 into 2, 24 oxygen. And here we have 11, so 24 plus 7, 35. Okay, already 11 here. 11 is here. Okay, 35. So minus 11 will get 24. So we need only 24 here. So I'll put 12. This is the balanced equation. Okay, so in the given data, this amount is wrong, so I'll put 12. 12 O2. Okay. Now, I think now it will come back. So that if you reverse the reaction, I'll get 12 instead of 35, I'll get 12. 12 O2. Okay. So it won't cancel actually, because I have only 12 here, 12 O2 here, right? So we'll get some remaining species, right? So 35. Okay, so what we get now is here we are 24. So 24. So this 12O2, let me cancel here itself. This 12O2, this 12O2 cancel. So we have remaining species as in the title here. I'll just cancel this 12O2 and this 12O2. So what is remaining? We have 12 carbon graphite plus 11 H2 gas plus 11 by 2 O2 gas, giving C12 H22 O11 solid. Now check the reaction whether it is completely balanced or not. 12 carbon, 11 into 2, 22 hydrogen. Yes, I have 22 hydrogen. 11 by 2 into 2, yes, I will get 11 oxygen. Okay, now see this reaction. This is very clear. We are getting 1 mole of the sucrose from the elements. Okay, we have carbon, hydrogen, oxygen. So we have taken the elements in their stable and common occurring state. Okay, now what is the enthalpy of this reaction? Very simple. We have added everything. Therefore, the enthalpy is supposed to be added. Okay, enthalpy also supposed to be added here. So if I add everything, what will I get? Listen. So if I add, here I have 3000 plus 3000. Here I have minus 4, this is plus 3000, minus 4722, and here I have minus 2659. You have to add everything. Right? Now these two are same sign, so I will add these two, then I subtract this one. Okay, yes. Yes, it gives me the value of minus 4381 kilojoule per mole. Okay, this is nothing but the standard enthalpy of formation of sucrose. Okay, standard enthalpy of formation of sucrose. Okay, so in the given question, 35 by 2 is wrong. So I just corrected it and then I balanced the equation accordingly. Okay, just go through this. Yes, this question, this is question number 7 actually. This question number this is question number 5. Just go through the reaction question. Enthalpy of reaction at 320 and at 340 Kelvin were found to be, okay, enthalpy of some reaction at temperature of 320 Kelvin and 340 Kelvin are available. Okay, so enthalpy of reaction is equal to minus 400 kilojoule. This is at temperature, let me take the temperature as T1, 320 Kelvin. Then another enthalpy is given, delta H. Let me take this as delta H1 and this is delta H2, which is 250 kilojoule per mole. 250 kilojoule per mole. This is at a temperature of 340 Kelvin is given. So what I did, I took this temperature as T1. At T1 temperature, enthalpy changes, I took it as delta H1. Similarly, at another temperature T2, I took the value as delta H2. Okay, what we need to do, we need to calculate delta Cp. Yes, we know very well, according to Kirchhoff's equation, you might have heard about this. According to Kirchhoff's equation, delta H2, right, equal to delta H1 plus delta Cp into T2 minus T1. Okay, we can use this formula to calculate. And here, this is actually a simple question. Why? In this question, they are asking just a delta Cp. So what you have to do, bring the delta H1 to the left hand side. So delta H2 minus delta H1 equal to delta Cp into T2 minus T1. Okay, now bring this T2 minus to the left hand side. So delta H2 minus delta H1 divided by T2 minus T1 equal to delta Cp. So we can calculate delta Cp by substituting the data here. So what is delta Cp? Therefore delta Cp equal to delta H2 is minus 250. Okay, minus delta H1 is minus 400 divided by T2 temperature is 40 and T1 temperature is 320. Okay, so you keep this minus 250 as such. This is minus or minus plus 400. 340 minus 320 is 20. And here if you subtract, you will get plus 150. So 150 by 20. Okay, 0, 0 cancel. So 15 by 2 or we will get 7.5 like that. Okay, 7.5. This is the delta Cp of the reaction. It's a very simple one. Okay, but you should remember this formula. This is called Kirchhoff's equation. If enthalpy of reaction is given in two different temperatures, then immediately this formula should come to your mind. Okay? Yes.